Hi, yeah, hi everyone. Thanks, Dr. Joe Perez, for the introductions. And I feel nervous going after Joe because he is such an energetic speaker. So I'm gonna try my best. So I'm gonna talk today about a topic that is I'm very interested in working on is machine learning compilers and how to bring machine learning to the edge. I think Dr. Perez also gave a great introduction about me. So I think I just want to reiterate that I'm working on a startup about real-time machine learning, and we want to chat about more about it. Please let me know. So I was never a good system engineer, and when I was in school, I was terrified of anything compiler related. But then the more I work on machine learning in production, the more I realized that it's really impossible not to touch on compilers. And I think I realized a quote from Sumit Chintala's the PyTorch. So he was talking about how for some years we were competing about framework like PyTorch versus TensorFlow, and the next battle he believe is about compilers, how to make machine learning models work really fast. So for the agenda today, we're not first going over the importance of machine learning on the edge, and then we talk about like why you need compilers, how compilers work, and for the last session, we talk about how we can use machine learning to speed up machine learning model. So the first topic, so edge computing is one of the phrases that have got so much traction in the last decade, and it's for good reason. So I just like to refresh the audience. Cloud computing, when a lot of computation is done on the cloud, like on the server, for example, AWS, GCP, Azure, and edge computing is when a large chunk of the computation is done on edge devices, which can be the phones, a tablet, a smartwatches, or it can be like it be in browsers. So example of the of machine learning models that run on the cloud are a lot of like smart assistants. So when you talk to Alexa, Siri, or Google Assistant, then all the speech recognition system will be run on the cloud, and then they respond back to you. Whereas edge computing example of something like the same as smart assistants, even though the most of the queries to smart assistants are done on the cloud, there's certain queries that are done on device. For example, when it's like OK Google, so OK Google will wake the Google Assistant even though the phone is not connected to the internet. Another example is a predictive text. So when you type on the phone, sorry, see, I said okay Google, and now my phone just wake up. So predictive text, like when you type on the phone, it will suggest you what you like to type next, or like unlocking the phone with fingerprints or faces. And I have the red the last example in red, because for the task of unlocking the phone using the fingerprints or faces, it's like that. It's very important to do it on device because a lot of people might feel unsafe to have all the biometric informations on the cloud. So there are a lot of benefits to edge computing. So the first is that when you do the computation on the device, then the application can work without internet connections or with unreliable connections. So for example, like when I was helping companies deploy machine learning models, a lot of them have very strict no internet policy. So like they, first of all, like the warehouse, they have like confidential information, so they can't connect the machine to the internet. So whatever applications you have to work within their locality they request. So there's a caveat to it. It's like, so the applications might be able to do computations on device, but the applications might still need external information from the internet to work. For example, when you do ETA estimations, like estimating the time of arrival, the computation might be possible to be done on the device, but you still need to connect to the internet to get all the traffic information to get the most correct, accurate predictions. Another nice thing about edge computing is that you don't have to worry about network latency. So if you have some model on the cloud somewhere, then first you have to send some the data, like the query from the device to the server, and then the server is gonna generate predictions, and then you send the prediction back to the device. So it's a round trip, and it can be very slow. And I have seen a lot of applications where the network latency is actually the bottleneck and not the inference latency generated by the model. So an example we talk about is predictive texting. So for predictive texting to be useful, like the recommendations have to be faster than the speed at which you type, because like if it's slower than the speed at which you type, then there's no point in using like predictive texting. Another benefit is edge computing means fewer concerns about privacy. So when so first of all, like you don't, because you don't have to send data over the network, there's less chance of the data being intercepted in the way, on the way. And another thing is that like cloud-based, so when you do things on the cloud, it usually means that a lot of people data are stored in the same locations. So if there's a breach to those locations, a lot of people will be affected. It also make it easier to comply with regulations. For example, GDPR requires like a lot of considerations when you ship data to the cloud somewhere. So there's a caveat to this is that like edge computing can help you reduce the concerns for privacy, but it doesn't eliminate concerns about privacy entirely. So one caveat is that when you tap all the data on a small device, it might make it easier for people to just like take the device and run away and get all the data. And I think the last benefit of the of edge computing, which I also believe is not believe like from observations, that a lot of the reason that push a lot of companies to it is that is a cost. So the more computation we can push to the edge, then the less computation we have to done as a cloud, and the less we have to pay for servers. And cloud bills are very expensive. So what I keep talking to companies, and they complain about like how expensive it is to run like how expensive it is to do things on the cloud. And I think there's a lot of Reddit threads and Hacker News threads where people just complain about like how one mistake almost cost them, almost like bankrupt them. So I think it's an interesting graph about the cost of the climbing cloud cost of different companies over the years. So because of the benefits of edge computing, many companies are heavily investing in making better chips, better hardware to go to run computation on device. So you can see like companies from big companies from Tesla to Google to Apple, like even Facebook, they're all trying to develop more chips so they can run machine learning models on device. And then also like many startups that have raised billions of dollars to develop better hardware. So okay, now we're talking about the importance of edge computing. We're talking about like why you need compilers and why is that related to all the edge devices, edge computing. So given given that there are so many different hardware, one question is that after you have developed a model using an arbitrary framework, how to run that model on an arbitrary hardware, right? So I think it's the questions of compatibility. So you have so many different frameworks. You can develop the model with PyTorch, TensorFlow, scikit-learn, MXNet, or like a new and hot framework on JAX. And there's so many different kind of like hardware, like GPU, TPU, phone chips, like ARM chips. Then how can you just run the model built with an arbitrary framework on an arbitrary hardware? As soon as a problem is a problem with performance. So in a machine learning workflows, you use a lot of different libraries. Like you might use like pandas, NumPy, PyTorch, and even those each library might have some certain performance, some optimizations within the library. There's actually no end-to-end optimizations across libraries. So there's one study by some researchers from Stanford when they found out that like a typical data science workloads using NumPy, Pandas, and TensorFlow run about like 23 times slower in one thread compared to hand optimized code. So if you hand optimize your code, you can make it run like so much faster. So usually in a company I have seen is just like usually they have data scientists and machine learning engineers develop workflow and then try to deploy it. And when things get slow, they start hiring optimization engineer to try to like boost the performance, the speed of their system. However, like the optimizations across libraries, across hardware can be very, very difficult. And the reason is that like different hardware backends have very different compute primitive and different layout. So first of all, if you want to do some kind of computation efficiently, you would like to leverage like in-memory buffer layout of the hardware to do that faster. And then like every single like type of hardware when do it differently. So we can see here like some of the layout of like different the layout of the memory layout of different hardware backend like CPU, GPU, and TPU. And you can see like they have different compute primitive. So first of all, like traditionally CPUs use scalar as the compute primitive. GPUs use vector like one-dimensional array, whereas tensors use like two-dimensional array as their compute primitive. And you also know that in deep learning models, you have like high-dimensional instructions, and you need to convert into like low-dimensional compute primitives. Um, yeah, so so it's really hard because you need to understand how each hardware backend is laid out so you can optimize our code for that backend. So what usually happens so far is that like for framework developers, when you if you want to build a new framework like PyTorch TensorFlow, usually offers support like support across a narrow range of server class hardware. For example, we say like let's try to get our framework to work really fast on like GPU, and whereas at the same time when for hardware vendors when they develop new hardware, we probably try to like offer certain kernel libraries for a narrow range of frameworks. For example, like NVIDIA, you will have people trying to optimize, like writing kernel to get the GPU to work really fast on like common frameworks. So a problem is that like you might have hardware lock-in, so that like, if you develop the model with a framework, you might have you might be stuck to a hardware that supports a framework, and also make it incredibly difficult for framework developers to develop new framework because now they have to like provide support for like multiple hardware backends. So that's where compilers come in. So compiling, optimize. So it's more like optimizing compilers. They do two things. The first, they help with compatibility, as in they lowering um, um, they lowering the model code into hardware native code. So lowering here just means just like generating hardware native code for your models. So it's not translations because there's really not one there is no one-to-one mapping from model code to the hardware native code. And another thing that optimizing compilers do is that it's help with performance. So in the process of lowering your model code into the hardware native code, so the compilers also optimize the model to run on the hardware. So it sounds like wonderful, and you might wonder like, so how do compilers do that? So let's back to the question. Let's back to the previous slide that we said like with compatibility. So we have like multiple backends, hardware backend, and multiple framework front end. How do we make a model run on an arbitrary hardware backend? So instead of like trying to get every single framework to work with like every single back end. So like, what if we have something like a common language or like a middleman, so that like we can convert any of the framework code into like this common language, and then you just need to generate from the common language to like the hardware backend. So like for the framework developers, instead of like generating like making it work for every hardware backend, you only have to make it work for this common language. And then similarly, hardware backends only have to work with the common language instead of with every single framework. So the common language is called intermediate representations, and there are different level of intermediate representations. So you can have high level. So we would call this IR because I'm not a native speaker and I have difficulty saying like long phrases like that. So you have like high level IRs. So which if you use TensorFlow, you're probably familiar with. So it's like a computational graph. So you have like basically like it's a graph of like how the computation is done on the model, and then you have lower level IRs, so which is like language agnostic, so something example of like LLVM or NVCC, and there's something in middle tuned IRs, which we're gonna go into in later. So I think one of the things I've been very curious for a long time is like how to optimize the models. So there are like standard compile optimizations for example like vectorizations, loop tiling, explicit parallelisms, and like doing cache. So here's a visualizations of how loop tiling works. So loop tiling is when you have maybe like a nested loop, and instead of like computing something like on the left, like doing the first row and then second row, you try to leverage how the memory you try to leverage cache to actually do it more efficiently. So instead of doing like first row and the second row, you can do it like something like on the right, and it's more efficient. And another thing is like operation fusions. It's also a very similar idea. Instead of so you can fuse different operators together so that you can do this at the same time and make it more efficient. Here's just like a graph to show like how operator fusions can improve the performance. So it can give you like up to like 2x speed up in certain cases. Another kind of optimizations is like graph optimizations, which is more general. So given a computational graph, you can maybe like do vertical fusions, like you fuse is like in vertical directions, or you fuse them in horizontal fusions, like in this example. And this can help you like do one pass through the computational graph faster. So it is actually like really hard because it's like this on the so even though they are like the common method of doing optimizations are like well understood, doing so is still very hard because all the optimizations has to be like hardware dependent. So it really depends on different processing memory cache latency hiding as layout above. It's also operator dependent because it's also depending on the operators or like the kind of computations you do in the model. And because like new models are being developed all the time, different ways of like combining operators, um there are new operators, new models all the time. So like every time there's some have a new models, you have to like think about like how to optimize that new model. And there are many different possible paths to execute a graph. So for example, like if you have three operator A, B, or C, you might want to fuse A with B or B with C or A, B, C together. So there are many different paths to execute a graph. So what a lot of companies do right now is they try to come up with like hand-tune optimizations. So it's like heuristics based. So like they get some like really experienced engineers who nobody can fire because like they are the only one in the company who knows how to do this kind of like stuff. It's real. So for example, like NVIDIA might hire some optimization engineer to optimize ResNet for the new Tensor Core GPU. So the problem with that is like is not optimal because it's heuristics based, and even though like a lot of heuristics can be very efficient, it's usually not optimal, and it can be like non-adaptive. So like first of all, like if you have a new hardware, new framework, new models, and you have to adapt the optimization to own these new things. So an idea is just like, what if instead of doing hand-tune optimization, we can use machine learning to do optimizations? So the idea is just like, what if we explore own possible paths to execute a graph to find the optimal path? So it can be like, um, so so like so like you can explore a path and you can run the path end to end to find out how long it takes to execute the path, and then you can just like choose a path is fastest. But it's like too slow because there are too many possible paths. So there have been a new research directions where we use machine learning to narrow down the search space to find approximately the optimal one. So you don't have to find like the really optimal, but can approximate the optimal path. So here's an example of like auto scheduler, like which is like what TVM does. Is like first you break the graph into different subgraphs, and then you predict how big each subgraph is, so you can allocate time for that graph. So like instead of like having to run the subgraph from end to end and measure them, you can actually predict how long it's gonna take to do the path. And then you predict like the optimal way to execute the subgraph, and then you can tie them on the subgraph together to execute the entire graph end to end. So like you can pretty familiar with so what I'm saying here, TVM auto scheduler, which is more general, and the QDNN auto tune. If you haven't tried QDNN auto tune for PyTorch, you should definitely do that. And here's just like some because we're running out of time, so let's run over like some nice result of how auto TVM work. It's clearly show so of course this benchmarking is really hard, sometimes can be hard to reproduce, and you sometimes have to take the result with a grain of salt. But here it shows that like tvm auto scheduler auto tvm actually run faster than hand-tuned kernels written by qdnn. Here's an example of show tvm compared to other optimization method on raspberry pi. And yeah, so TVM actually an open source project, and if you want, you can actually install it using pip install here. So one catch with using TVM though, is because it's using machine learning, it explores a lot of possible paths, so it can be pretty slow for the first run. So it can be like hours, even days. But the nice thing about it is that like you only have to compile the model once. So if you're in the setting when you have to deploy the models like multiple devices, then you just compile the model once and have even like get a little of speed up. But then like across multiple inference, it can be a huge saving. So yeah. Anyway, I think now it's time for Q&A, and thank you so much, everyone. If you have any questions, please let me know.
All right, Chip, thank you so much for presenting that information. Very useful. Um, let's see, look at questions that we've got here. What can happen when you use test data instead of actual data with I can't say it. You think you can't talk. Yeah, machine learning. I can't say it right. Test data
Yeah.
instead of actual data with machine learning.
Sorry, can you repeat the question? Like, what happened
Sure.
when we use test
What can
data?
yes, what can happen when you use test data instead of actual data with machine learning? I guess how can that
Uh,
throw off the bias maybe or throw off the
what do you want to? Okay, so I think I'm a bit confused with the questions because what are you using test data for? Because I think in machine learning you use test data to evaluate the model, or do you mean test data as in toy data?
um yeah, that's a good one. Tell you we have let's see, Pooja has just uh checked in. She says she can take that question later because it's probably more in the context with what she'll be talking about. All right. Our next question. This one says I've heard the term data mining thrown around quite a bit with machine learning. What's the difference between the two?
Oh, that's an interesting question. So data mining versus machine learning. So I think I can see the confusion because they are both deal with a lot of data. So I think of data
Hmm.
mining. I think data machine learning is actually a subset of data mining. So data mining is when you have a lot of data and you try to gain and generate insight from the data. And whereas machine learning is a subset of it because you also like leverage data to generate like predictions or help you understand the data in different ways. So yeah, I think data mining is a very general, big field. It's like anytime when you want to gain extract information from a large amount of data.
Okay. And let's see here. There's
I think
always.
Pooja
Oh yeah, go ahead.
has a response for that. Yeah, Pooja
Right.
has a
Okay.
great response for that. Yeah.
Okay. Very good. Very good. Uh, Yeah, it says data mining uses techniques created by machine learning for predicting the results, while machine learning is the capability of the computer to learn from a mined data set. There we have it. All right, excellent. I hope this answers your question. And last question, unless another one comes in, there's always going to be bias when looking at data and issues and so forth that you're trying to resolve. What is the trade-off between bias and variance?
Um, it's very interesting. It's a it's it will all like you said, it all will always be a trade-off because there's certain algorithm and techniques will have to reduce a bias, but there's certain techniques will have you reduce variance at the cost of like higher bias. So so yes, so I don't think there would be like a way around that, but I guess I think understanding the trade-off also help you choose what is the kind of algorithms that is
Right.
best for the solutions. Yeah. I
Yeah,
think there's
it's
a lot of, yeah, sorry.
no, no, go finish your thought. I'm sorry.
Yeah, so I think there I think understanding also help you to like I think Andrew Ng has a pretty great lectures on that, where also help for example like if as a certain if the algorithm is very much like high bias, like having more data is maybe
Right.
like having so it's have you decide whether you need more or less data, because like really depends on whether the model is like have higher variance or higher bias. You could need to decide the amount of like data that correspond to that.
I couldn't agree with you more, Chip. I mean, either you've got erroneous or overly simplistic assumptions. That's going to lead to your bias. And variance, you've got too much complexity in your learning algorithm, right? It leads to the algorithm being highly sensitive to high degrees of variation. So, yeah, I'd much rather have that. That seems to make more sense to me than to make erroneous assumptions about the data when you're putting it through the models. So, yeah, components of reducible error. So, all right, very good. Well, Chip, thank you so much for being with us this afternoon. What's the best way for people to connect with you?
So yeah, so I think I'm not sure you can still see my screen, but it's also on my Twitter and my email. Yeah, just shoot me an email anytime. Thank you so
Sounds
much for
great.
having me.
Absolutely, Chip. Thank you for being here, and wish you all the best.
Thank you. Have a nice day. Bye
All
bye.
right.